So one can also find similar examples of inductance calculation for toroid. We are not going to do that one. Instead, go to a different example which is very interesting, because this was one of the commonly used transmission line or a cable that about 15 or 20 years ago people were using everywhere to connect their television sets to the antenna, and this is called a two-wire line. This was around 300 ohm line that was normally used. Okay. With two-wire line, we actually have two wires, long wires which are carrying certain currents. So you have a current I and then you have a current minus I, that is current in one path and the return current in the other path. Now I want to find out the magnetic flux linking, right. So I take this current which is along positive I to calculate the magnetic field because of that, and then I will do the appropriate integration to find out what is the flux. First let us write down the magnetic field. Magnetic field is of course along the phi direction, but for this plane that I am considering I do not really have to talk about phi, because this distance is r, and then the magnetic field at this particular point is given by H is I by 2 pi r, where r is in this plane. Okay. Although we know that these are actually along the phi direction, right, but for this plane that I have cut away, this is enough for me, I by 2 pi r. If you really want to talk about the magnetic field, you actually have to insert this phi direction everywhere. Okay. So the magnetic field would be around at all points coming out of this particular page or particular screen. So magnetic field is I by 2 pi r, and I can find out what is B field. B is mu 0 I by 2 pi r, assuming that the two wire line is actually kept in air. Okay. So this B will be mu 0 I by 2 pi r, and the magnetic flux will be integral of B along this radial direction, right. I need to again consider the similar thing. So I have to consider 1 meter around the z axis if I am considering the current to be along the z axis, and then whatever the value of r that can go from here. So if I take this as the origin, then this would be 0, and let us say the separation here is d. So my r would seem to indicate to go from 0 to d, right. So plug in those values B, dr. This would be again the flux linkage per unit length, right. I am removing the integration with respect to z here. So this will be given by mu 0 I by 2 pi is constant. So let me pull this outside and put the integration limits of 0 to d, 1 by r and dr. Is that okay? Now clearly we run into this problem, right. See, we will run into a problem here, because if I integrate this, I know that integration of 1 by r is log r, and if I try to apply the limit of log to 0, right, try to find out what is log 0, that is undefined. So it turns out that I am actually running into problem if I take r is equal to 0. So what is actually happening? Is our mathematics incorrect? Did we actually set up the problem wrongly? Our mathematics is correct. It is giving you what it is supposed to give, except that we have forgotten a very important characteristic of wires. No wire will have 0 cross section. Wires actually have a finite cross section, right. So because of that, the proper way to have written down this two wire line would have to be like this, with let us say a cross sectional area of A, and this line will also have an equal cross section, let us assume that, and therefore my integration should have begun from this inner conductor to this inner conductor. Between that two conductors is what I am supposed to find the flux through, right. So the integration limits must be changed from 0 to A and from d to d minus A, right. And if I do that, I will get the exact expression. So and if I also take this current I and divide it onto the left hand side, I get the inductance per unit length as mu 0 by 2 pi log of d minus A by A, and in case d happens to be much larger than A, the separation happens to be much larger than the cross section, which is almost what happens in a practical two wire line. This can be approximately written as mu 0 by 2 pi into log of d by A. Okay. A slightly better result can be obtained if I replace this d minus A by the geometric mean of these two distances. Okay. So I can do that, but I will get a very small improvement, not really worth the effort. Now you might ask, for the coaxial cable that we considered, we did not actually talk about finite cross section at all. There was a finite cross section for the inner conductor. The inner conductor was having a radius a, and that was the finite conductor that we actually had to take into account. Similarly, the outer conductor of the coaxial cable will also not be at 0, it will also have 0 cross section, but it will also have a certain finite cross section. Then why have we neglected those effects in the coaxial cable? Strictly speaking, whatever we derived for the coaxial cable is wrong, because we have neglected the cross section, and I should not have been neglecting those cross sections. However, there is a very good reason why we have done so. When you look at this coaxial cable, this is normally operated, although at low frequencies it is operated, at high frequencies, a few megahertz or few hundreds of megahertz when you are operating, current does not flow in the entire conducting surface. Current actually gets concentrated or pushed to the walls, okay, on a very thin layer called as skin depth. This skin depth actually starts to become very small as the frequency increases, and if operate this coaxial cable at around 100 or 200 megahertz, you will see that the current is actually confined to a thin walled area around the inner conductor, okay, and similarly the current will be confined to outer conductor on a very thin layer. This layer is around few micrometers, and therefore there is not much that this result can be affected. So for coaxial cable we did not really include that term, but strictly speaking one has to include. But when you try to include that, you will run into a problem of partial fluxes, okay. Just as you have run into a problem of partial fluxes here, but we have not really talked about it, there will be partial flux problem, and that would be mathematically slightly tricky to take up into account. And that is the reason why we neglected for a coaxial cable what happens for that one, whereas a 2-wire line is normally not used at those high frequencies, okay. Alright, so we have talked about finite cross section and partial flux has been mentioned, but we have not really talked about what partial flux is. It is perhaps interesting for us to take that partial flux and discuss it a little bit more in the context of 2-wire line, okay. So we are going to do that one now. So we will discuss partial flux now. To do that one, we need to go back and understand that filaments that we have assumed or conductors that we have assumed which had 0 cross section cannot really be true, and we have to take into account this finite cross section of the conductors. How do we do that one? Well, if you take open one of the filaments over here, so let me try and isolate a filament over here. So if I try to take the filament over here and then look at it in a microscope or in a very exaggerated way, what I would actually see is that this filament actually has a finite cross section. So this is what from the top view, for example, this is the top view of the conductor that we are looking at, and I am assuming square cross section just for simplicity, although this is actually a circular cross section that I should have assumed. But nevertheless, if you zoom in onto a circle with a very large zooming factor, it would essentially resemble a square, and that is what I am looking at. Now within this one can actually imagine this entire thing is a conductor, okay, this is not hollow space, this entire thing is a conductor, but I can actually kind of imagine this to be composed of multiple filaments, okay, and over a particularly small segment that I am interested in, right, the amount of current that is carried by this would be just a small amount of the current compared to the overall current I, right. See, if the entire cross section S, a small s, carries the current, then the current carried by this differential element will be di, correct. It would only be carrying the total, a fraction of the total current, okay, and this small section within this cross section S has a cross sectional area of ds, and then if you want to obtain the total current and the total cross section, and to do that one you have to simply sum all the contributions or essentially integrate the contributions, okay. So if you can find a way to take into account the fact that conductor has a finite cross section S, and this finite cross section S can be composed of multiple smaller segments of cross section ds, each carrying a current dI, then we will be able to talk about partial flux or flux that is linking with conductors of finite cross section. Okay. To do that one, let us actually review what magnetic flux linkage was. Magnetic flux linkage was integral of B dot ds, right, the magnetic flux integrated over ds. Now B can be related to A, the magnetic vector potential, and I can replace B with del cross A and replace this del cross A dot ds, the surface integral, with a line integral over vector potential A. This is one of the places where vector potential is really helpful in dealing with calculations rather than the direct magnetic field itself. Okay. So this A dot dl is what I have, but where is this A dot dl getting integrated into? It is actually getting integrated over the entire circuit, right. So if for example I have this circuit, okay, so in between I have to make some space. If I have a circuit, right, with very small segment here, right, call this as dl, and there will be a magnetic vector potential A, right, and this is the filament that I have actually considered and expanded over here, right. So for this loop, okay, this loop actually forms a certain surface as well, right. So the B field that would be linking has to be found over this surface. These gaps being very small, I can kind of neglect them. So I can also define this entire surface as capital S. This is the region over which I have to integrate the magnetic field, or this would be the periphery over which I have to integrate the line integral of magnetic vector potential A. Okay. So why have I written like this? So let us say there is some current flowing, then this current would actually be linking the second circuit, right. So this would be the current that would be linking, right. There could be some magnetic field that would be linking, there would be some magnetic field that could be linking over here, and this is this magnetic field that we are actually interested in. So if you want to calculate the inductance of this loop, the square loop or the rectangular loop, I have to find out how many flux lines are actually linking to this loop. Okay. So for that reason I have to consider this big surface S and I have to consider the corresponding contour C. Okay. So this is the integration that I am actually performing. Now this integration that we have, which I have shown, is actually applicable to only one filament, right. So you imagine that the filament actually has a cross section that is not 0, and there are a lot of filaments inside. Each filament there will be a line integral A dot dl which is going over the entire closed circuit C, and then you are now summing up those over the cross section S. So there are two integrations going to happen. One integration will be integration over the big surface S or equivalently over the big contour C, right, and then there will be a second integration over the cross section itself, because you have to sum all the contributions of the filaments inside there. Therefore, the magnetic flux properly for wires with finite cross section will involve two integrations, one integration over the smaller S which is the cross section of the wire, and then the integral of A dot dl. Now instead of writing this over the contour C, I am going to write this one over the big surface S, just to indicate that this surface S is the periphery surface, the surface bounded by the peripheries of the wire that I am considering. Remember that this capital S is actually bounded by this capital C curve, okay, and I can write this as AL, okay, where AL is the component of the vector potential along the line integral dl. So I can write this as AL, and there is dl, and there will be cross sectional area also, right. So the cross sectional area actually carries a current of di, a fractional current of di by I, okay. Now I can write down what is L here, the inductance will be lambda by I. So I multiply by I here, and then I get two integrations, smaller integration over cross section, larger integration over the loop, and then AL dl di by I, okay, I square, right. So it would be di by I square. So this is the expression for inductance that we are looking for. However, this expression can be simplified slightly if you assume that the current density J and the current I as well as the cross section are all constants. Okay. J of course is the one that is coming out of this particular conductor, and J is given by I by S. The current density is given by I by S. Therefore, di by the fractional current that is carried by the element of cross section ds will be di, which is I by S, the current density times the cross section ds. Therefore, I can rewrite di by I as ds by S and substitute that into this expression, okay, into the expression for L, and when you do that you are going to get L is equal to integral of S, integral of the capital S, AL dl and ds by S into I. This is the expression that we are looking for the inductance, okay, and we can use this expression for the 2-wire line. We will do that one, but before that I need to consider the vector potential for a line carrying a current I of finite cross section, okay, and if I know that one, then I can use that value for the vector potential and calculate the inductance of a 2-wire line, okay. So, the first job would be to try and find the vector potential. This vector potential clearly will have two components, right, because this would be the conducting wire that we are considering of cross section or of radius a. There will be magnetic vector potential inside and magnetic vector potential outside, okay. So, outside the current enclosed is I, and you can actually write down the expression for magnetic vector potential A0, or you can start with the magnetic field B and then come and calculate what is A0, okay. So, outside B is actually given by mu 0 I by 2 pi r if you are at a particular distance r over here, or let us say I want to use r for a different reason. So, I am going to write this as mu I by 2 pi rho. So, I am actually at a distance of rho here, okay, and I am actually considering the current distribution at this particular point, okay, the line element at this particular point at a height z above the horizontal plane, okay, and the distance between the current element to this field point will be small r. This is my notation for this particular problem. So, the magnetic field around this will actually be along phi direction, and this will be given by mu 0 I by 2 pi rho. From this you can actually calculate what is curl A. Curl A should obviously have only the phi component, right. So, it does not have any other component, and you will actually see that the phi component is del A z, right, minus del A z by del rho along phi, okay. So, from this you can actually integrate for z, and you get Az of mu 0 I by 2 pi C0 some constant minus mu 0 I by 2 pi log of rho, okay. So, let me not show the derivation over here, because as such we want to finish the calculation for the inductance, but I will leave this as an exercise and guide you how to do it step by step in the exercise. You can actually show that the magnetic vector potential outside is actually given by this mu 0 I by 2 pi some constant C0 minus mu 0 I by 2 pi log of r. So, clearly this constant C0 one has to choose carefully so that there is a proper 0 reference for the potential, okay, and you cannot choose infinity as the potential, because if you choose infinity as the potential everywhere will also become infinity, that is infinity point cannot be chosen as reference for 0 potential here, okay. So, this is one result to keep in mind. Similarly, you can actually find out what is the internal AI, that is the vector potential inside the region, and this turns out to be some constant Ci minus mu 0 I by 4 pi rho by a whole square. So, if you are considering inside, then this would be rho by a whole square. The reason why you get a rho by a square is because the current density inside the conductor is actually proportional to rho square by a square, okay. Again, this will be developed during the exercises, so do not worry if you are not able to get this one at this point, okay. You will have the opportunity to derive these expressions for yourself, okay. Now that we have found out the potential inside and potential outside, all we need to do is to select appropriate value for reference potential, and you can choose any circle value or any value of rho as a reference potential, and if you choose rho equals to A, that would give you the one possible solution, that is a simplified solution where I am setting the reference for A to 0. Okay. So, if I set rho equal to A and take that as a reference for A equal to 0, I have to choose C0 equal to Ci so that I actually maintain the continuity of vector potential. Okay. So, if I do that one, then so if I remove this one, you will see that the magnetic vector potential can be written as minus mu 0 I by 2 pi log of rho by A for rho outside A. So, this is the outside potential, and for inside you have mu 0 I by 4 pi, sorry not 2 pi, this is 4 pi 1 minus rho by A square. Okay. This would be for A less, sorry 0 less than A, that is inside. Okay. So, inside the vector potential is positive and then goes to 0 at rho equal to A and then goes to negative value. Okay. Now, with these expressions we are ready to calculate the inductance of a 2-wire line. For simplicity, let us assume that their center to center spacing 2b is much larger than their radius A. Okay. Each of them have a same radius A, and now I want to calculate, and this left cylinder carries a current I plus I and the other current carries a minus I, because one current is going and the other current is returning. Okay. Now, the flux that is linking to this left one, which we call as C1, and the right one, which we call as C2, actually has two components. One, because there is an internal A field, right, internal vector potential AI, and then there is an external potential A0 because of the circuit C2. So, the contribution at any point or any cross sectional area of this one that you consider, okay, will have two components, one internal A field, okay, and an external A field. Okay. So, this fellow, let us locate it at a distance of rho 2, but because we have assumed that center to center spacing is much larger than A, rho 2 is approximately 2b, and to find out what is the vector potential that is appearing at this point, let us call this as point Q. So, at this point Q, rho 2 is 2b, and you can actually obtain this by substituting for 2b in this expression for rho, right. For the vector potential A, if you see, there is factor of rho there, and you substitute rho is equal to 2b and take I to minus I. So, that will give you the vector potential A acting at this particular point. Okay. Now, what is the direction for line element? Line element direction is along dz, right. Again, in the previous, for the 2-wire line case where we assumed that integration along the z axis is 1 meters, we will do the same thing here, and therefore, we do not really have to integrate over the surface S, okay, the larger surface S, because I am considering flux linkage per meter. Okay. So, therefore, the integral that I have to evaluate for L will be small integral only, because you can imagine that this is one filament, one filament, one filament, one filament, and these are all different filaments that I can imagine, each having a cross section of ds kept at these different points. Then integrate this one AL dl, right, d small s by is is what I have, right. So, this is the integral that I am going to evaluate. So, as I said, I have removed the outer integral because that would be only integration along z axis, and we are going to consider integration for 1 meters. Okay. So, if I do that one and then push this, when I remove that integral, the dl will also go. So, I only am left with AL ds by is, and this inductance will be in Henry per meter. Okay. So, this is the inductance that I need to calculate. If I substitute for AL, this integral splits into two parts, correct. For the second term, that is contribution from the external, from the circuit C2, the contribution will be mu 0 I by 2 pi log of 2b by A, and this would essentially be constant, okay, multiplied by the cross sectional area S will be the value for this second term, right. And as far as the first term is concerned, I have to consider A internal, okay, that would be given by this expression mu 0 I by 4 pi 1 minus rho by A square, and then integrate over that cross section, and for that the cross sectional is actually proportional or given by, so this is for the cross section ds is given by 2 pi rho 1 d rho 1, right, because this is the inside integration that I am going to do, and this here I cannot neglect, and by taking rho 1 is equal to a. So, I carry out this integration over the first term, so that I obtain the total integral. I take this small s to the left hand side and multiply by that one. So, I am left out by just integrating al ds by I, okay, and since there is a denominator I and numerator I in both the terms, that I will cancel out each other. So, I actually am left with 0 to a, there is a 2 pi rho 1 d rho 1. What is the field inside? Field is mu 0 by 4 pi minus rho 1 by a square, okay, plus the second term. The second term is simply mu 0 by 2 pi, I cancels out, log of 2b by a into s, that is the area, cross sectional area that I have already integrated. So, if you evaluate this left hand side integral, you will actually see that this will be equal to 1 by 4, okay, mu 0 by 2 pi, from mu 0 by 4 pi it becomes mu 0 by 2 pi, and then there is 1 by 4 plus the second term, which is mu 0 by 2 pi log of 2b by a Henry per meter. This is the inductance of this parallel 2 wire line with finite cross sectional areas, okay. So, there are two terms, one term because of the internal A field and the other term because of the external field, okay. And in the 2 wire line that we actually calculated, we took 2b is equal to d, and then this is essentially the expression that we obtained, right. So, you actually had, if you go back and check, the expression that we obtained for the inductance per unit length was actually mu 0 by 2 pi log of d by a, right, where d was 2b. So, this is how we obtained the inductance for a 2 wire line, which is a simpler case than that of the inductance that you can obtain from a slightly more sophisticated value, okay. If this has actually given you an idea that the analytical expressions are sufficient for us to calculate inductance for all these different geometries, you should be sadly mistaken, because if I change the problem from circular conductor to a square conductor or maybe a slightly different sized conductor, you will be stumped, because no amount of analytical calculations can be applied to these weird cross sections, okay. Although this may not really seem to be so weird, because when you fabricate a 2 wire line, you would expect a nice circular cross section, but what you would actually get is some sort of a deformed cross section, right. So, and if you want to calculate exactly an analytical expression, then you would not be able to do that, and people have not been able to do that, because that is a lot of complexity, that is lot of complexity, and there is no guarantee that if I change the cross section slightly, that result will hold. So, there is no general formula for a general cross section, that is what I am trying to tell you. And secondly, this also is the reason why one has to go to numerical methods. We have been talking about numerical methods, but we will introduce numerical methods in different module. There you will calculate magnetic field numerically, from there calculate inductance numerically, okay. So, however, you have to understand where one can put in some approximations, right, to obtain quickly a value for inductance, and then if you want to obtain qualitatively better answers, quantitatively better answers, then you have to employ numerical methods or solve the complete electromagnetic problem.